Welcome back to the Professor's Du Bois channel. I am Professor Victoria and this is Professor Corey, and today we're going to be talking about assigning oxidation numbers.
So in our previous video, we were really focused on this one reaction where we would put solid zinc into a copper nitrate solution and we could form solid copper on the zinc. And if we wrote this as a net ionic equation, it was really easy to see that the solid zinc that had equal number of protons and electrons went to the ion, and it's a positive ion, so it lost electrons. Likewise, we could see that the copper gained electrons to form the copper solid, and this is a redox reaction. Unfortunately, many of the reactions that we'll be looking at are not that easy to see who gained and lost electrons. So there has been a system put in place to help us with this.
Yeah, so we assign oxidation numbers to each atom in a compound or the element. That would be 0, but we assign oxidation numbers to each type of atom and we compare them from the reactant side to the product side and see if it's the same. If it's the same, it did not lose or gain electrons. If it's different, then it did. These are not just ions though. We assign oxidation numbers to all of the atoms, even if it's a covalently bonded compound. So there's a bond and it is a shared electron. Those electrons are shared between those atoms, but for this purpose, we assign those electrons to individual atoms in the compound. So let's take a look at what we're talking about here.
There's a set of rules and they're almost kind of cryptic, like they're all good and
you can learn them.
But it's just kind of a weird, I feel like I'm part of like a secret code here.
Ooh,
so
I like that.
So here's rule number 1. Each atom in a pure element has an oxidation number of 0. So this kind of makes sense. Back to our iron solid, if it has the same number of protons and electrons, it's going to have a 0 charge, and that makes sense. Now, our diatomic elements, each oxygen in that element, or in the diatomic element, has an oxidation number of 0. So that's a 0 as well. Rule number 1.
Rule number 1. Elements, 0. If it's an ion, the oxidation number is the ion charge. Well, that's easy. So that goes back to our simple example of our zinc and our copper. Those went to actual ions. So that's why it was so easy to see who gained and who lost. So there's another simple rule.
Okay, here comes the good stuff. When we have a compound, the halogens, that's group 17 or 7A, they have an oxidation number of -1. But there's an exception. So if chlorine, bromine, or iodine are combined with oxygen or fluorine, their oxidation number may be different.
Oh, fluorine's always -1.
You'll enjoy that one.
Fluorine's always -1.
That'll help you.
But these guys might be different. Okay, so oxygen is almost always a -2. Almost always. So that's going to help us assign the oxidation numbers of other species in the compound, knowing that oxygen's -2. There's one exception, and that's the peroxide ion. So if we're looking at like hydrogen peroxide, okay, that's one that might come up. You might see that example. In this case, our oxygens are -1. So each oxygen is a -1.
And I think that hydrogen peroxide that's probably where you'll see that.
Yeah.
It's not that common. Okay, so hydrogen can combine with nonmetals, in which case we assign it an oxidation number of +1. But it'll also combine with metals. In this case, we assign it an oxidation number of -1. So we've got a couple examples. CH4, we assign that a +1 because it's with the nonmetal carbon. With the lithium hydride, LiH, the hydrogen would have an oxidation number of -1. So it's important to know that distinction between metals and nonmetals with hydrogen.
Yeah, and if you think about it, if you think about the nonmetal is usually something that wants to gain more electrons. So if hydrogen is combined with a nonmetal, then we're going to allow those electrons to be like as if it was just on the nonmetal. And that would leave the hydrogen as a positive charge. Okay, so here we go. The sum of all of the oxidation numbers have to equal the charge on the species. So if the species is just a neutral compound, then all of the oxidation numbers are going to add up to 0. So I'm going to show you this with the first example, and we're going to use our rules for the ones that are always the same to figure out the rest. So for this example, I like to put my oxidation numbers up on top of my species, my atoms, and I do my math down below. So in this example, I'm just doing the CO2. Since it's a neutral compound, it's going to add up to 0. So I'm going to do my math down below. And if I think about my rules, oxygen is almost always a -2 unless it's with a peroxide. This is not the peroxide ion, so I'm going to say each oxygen up top is a -2, but I have 2 of them. Since I have 2 oxygens, my math down here is a -4. So my carbon is the one I have to figure out. So I have something -4 equals 0. Well, that's going to be a +4. Once I realize my total charge, I look to how many carbons I have. I only have 1, so that +4 is all on the carbon.
So our oxidation numbers are +4 for the carbon, -2 for the oxygen. And you were talking about the neutral compound, and if you're confused, like, how do I know if it's a neutral compound? Well, if it's not, you'll see a charge, and that'll be in the upper right, like in this next example. So this, it's polyatomic ion, has a total charge of -1. So this is all going to equal -1. And again, we can kind of lean on oxygen pretty heavy here because we don't have that peroxide situation. So the oxygen is going to be -2, and I have 4 of those. So my net charge from the oxygen is -8. So I just have to, do some math here. What -8 equals -1, and that's a +7. So my chlorine has an oxidation number of +7.
Just like in our rule where we said the halogens are almost always a -1, unless
except
they're with these oxygens.
And that's a good example.
Okay, back to a neutral compound, and in this case, if you have an ionic compound, you have to think about your monatomic ions. So potassium is a +1 ion. So if I have 2 potassiums, that's +2. And then our oxygen rule was a -2. But we have 4 of them, so that's a -8. So +2 plus something -8 equals 0. So this is a -6, so this must be a +6. Then you have to go back up and say, how many chromiums do I have? And they are the total of 6, so there's only 1 of them, so it's a +6.
Okay, so the oxidation numbers in this case, potassium +1, chromium +6, and oxygen -2.
You got it.
So before we were predicting products by doing double displacement reactions. Redox reactions, we can't necessarily predict the products, but we can recognize if the reaction is a redox reaction. And the way we do it is we just assign oxidation numbers to all the elements in a reaction. So we have to know the products and the reactants. And if we see a change, we know it's a redox reaction.
Okay. So, is this a redox reaction? This is a very real type of problem that you're going to see on exams and such. And I like to just get the low-hanging fruit first. So, I want to identify all of the elements. So, here I have sulfur. And on the other side, I have nitrogen. So, those are easy. I like to do that first. And then we go and assign oxidation numbers to all of the other elements and then see if we see anything that's changed. So I'm just going to start with the N2H4 here. And we've got a neutral compound, so that's going to total 0. I do my math down below and I put my oxidation numbers on top. So hydrogen is with a nonmetal. Nonmetals want those electrons, so it leaves the hydrogen as a +1. We have 4 of them. So the positive side is a +4. So something +4 equals 0. Well, that's a -4. But there's 2 nitrogens. And that positive or that -4 is distributed across both of those. So nitrogen's oxidation number is a -2.
So we can already see that nitrogen went from a -2 to a 0. And that is a change. So we did.
So we already answered the question.
We lost electrons. So we know we have a redox reaction. But if something loses electrons, something had to gain electrons. And we need to know that too.
Yeah. And the question will probably ask you that. What is oxidized? What's reduced? What's the agent, right, of change here? So we've got, this is an ion. Look at that. It's hydroxide ion. So this is actually a net ionic equation. This isn't a complete molecular equation. So, oops, look at that.
And also,
zero.
And also, you would not be able to predict those products. You know, if you were given these reactants.
At this point, no, right?
Right.
Hydrogen with a nonmetal is +1. So that's a plus. Something +1 equals a -1. That's -2, but our oxygen's always a -2 unless it's peroxide anyway. Notice how I didn't involve the 4. Those coefficients are just balancing for mass. It has nothing to do with assigning oxidation numbers.
We're concerned about charge here these days.
We are. This is an ion, so this -2 is the oxidation state of sulfur. So here we go. Look at that. 0 goes to a -2. There's our other change.
Gain 2 electrons.
And we have a +1 for hydrogen and a -2. Let's just make sure that that's neutral. We have 2 +1s, so that's 2 times a +1 plus a -2. Yep, that equals 0.
And we didn't even need to do that, the water, but that was good practice.
Sure.
And it's just important to realize that if we have a loss of electrons, there has to be a gain somewhere as well. So we have to identify both of those.
So nitrogen lost electrons, right? So this N2H4, the nitrogen lost electrons, Leo, so this was oxidized, and it was the reducing agent.
Right. And remember, these are the reactants. The reactants are oxidized or reduced. So if something was oxidized, something must have been reduced, or something lost electrons. In this case, it was the sulfur.
Sulfur was reduced, and it was the oxidizing agent.
And I didn't even think about it. Like you mentioned with those coefficients, you don't account for the coefficients when you're doing this. It doesn't matter. That's just for mass.
Yep. And balancing redox reactions are another whole topic. Let's practice. Try to assign the oxidation numbers to each of the elements in the following. And the second one is an ion, so that has to total, they're all going to add up to a -2. And the first one, they'll all add up to 0. Pause the video and give it a try.
Okay, so there's your answers. Hopefully you got those correct. If you did, you're well on your way to being able to do this. It's not that bad. There's just a lot of strange rules, but you're in the know. Yeah.
So you assign the oxidation numbers to all of the elements in the entire reaction, and then you can look and compare from the reactant side to the product side to see if we are changing oxidation numbers. If we are, it is a redox reaction. And then you can identify what species is losing electrons and which species has gained the electrons. Thanks for watching.
Yeah, thanks for tuning in. As with all of these new concepts, a little practice goes a long ways. So we do have some sweet sheets for you to practice on. And good luck.
Bye-bye.